All right, so we continue with describing the geometry of orthogonal operators. And let me remind you what we have proved last time. So we have established the existence of invariant subspaces of dimension between 1 and 2. Okay, so this was the first step towards our general theorem, which will tell us that all orthogonal operators are compositions of rotations and reflections. Okay, question about the recording here. I apologize about that. There was a technical issue because in the room, so that it didn't get recorded on Friday. So I posted the lecture notes. You can see exactly what material was covered in the lecture notes. I was following it pretty closely. Okay, so yeah, sorry about this. I'll make sure to record it next time. Okay, but to return to our topic, so let me remind you what we have proved last time. So we have proved this lemma, which is crucial for carrying out the analysis in the higher dimensional situation. So the lemma says that if V is a real vector space, you see we are not even using the inner product structure in this lemma, just a vector space, okay, non-trivial, and we assume that the dimension is finite as usual, so the dimension of V is less than infinity, and assume that T is a linear operator on V, okay. Then there exists a T-invariant subspace W of V such that the dimension of this subspace W is either 1 or 2. Okay, so we have proved that we can always find such a subspace. So today we are going to utilize this lemma to prove a stronger result, which tells us that in fact we can write the whole space as the direct sum of subspaces with these intermediate dimensions, which are T-invariant moreover. Okay, so this is going to be theorem 646. So the situation is the same, but now we have an inner product space. So let V be a real inner product space, okay, still non-trivial and finite dimensional. Okay, and let T be a linear operator on V, which is orthogonal. Okay, then there exists pairwise orthogonal T-invariant subspaces W1 through WM, WM subspaces of V, such that we have the following two conditions. So A, each of these subspaces Wi has dimension between 1 and 2, so it's either 1 or 2 for all I between 1 and M. And B, we have that the whole space V can be written as a direct sum. W1, direct sum with W2, etc., direct sum with WM. Okay, so you see the previous lemma just tells us that there exists a single subspace W, which is T-invariant and has this intermediate dimension. So now we strengthen it to say that in fact the whole space can be written as a direct sum of such subspaces. Okay, as long as T is orthogonal. All right, so let's prove this. So we're going to argue by induction using the previous lemma. Okay, so by induction on the dimension of V, the whole space. So the first case, the base case, is when the dimension of V is equal to 1. In this case, the conclusion is obvious because we can just take W1 to be all of V And then, of course, this W1 satisfies the requirements in A and B, right? Because it has intermediate dimension, it has dimension 1, so it is between 1 and 2 because it's just 1, and it's equal to V. Yeah, so we get the case dimension V equals 1 directly. So now we should prove the inductive step. So next, assume that the theorem holds. Assume that the theorem holds whenever the dimension of V is smaller than n, okay, for some fixed integer n greater than 1, because we already proved it for 1. So now assume n is 2, 3, etc. Fix one of those, okay, and assume that the theorem holds for all vector space, for all real inner product spaces of smaller dimensions. All right. So suppose that the dimension of V is equal to n. Okay. So we can apply the lemma. So by the lemma, I mean the one I just wrote here, yeah, this lemma. By this lemma, we know that there exists a T-invariant subspace. Let's denote it as W1. So T-invariant subspace W1 of V, such that the dimension of W1 is between 1 and 2. Okay, so the lemma guarantees existence of such a subspace. All right, so now if it happens that W1 is equal to V, then we are done. Okay, just as in the base step of induction, if already the whole space has dimension between 1 and 2, we are done. All right, so otherwise, we have that the orthogonal complement of W1 is non-trivial. Okay, so why? Because we know that the dimension of the whole space, so remember this is a basic property of orthogonal complements. So the dimension of the whole space is given by the sum of the dimension of W and the dimension of the orthogonal complement of W, right? So now, since we're assuming that W1 is not all of V, it means that the orthogonal complement has dimension greater than 0, right? So it means that, in particular, it's non-trivial. It's not just a 0 vector. Okay, so we know that the orthogonal complement is non-trivial, all right? But then we have that the orthogonal complement, W1 perp, is T-invariant. And moreover, taking the restriction of the operator T to this subspace, W1 perp, is also orthogonal. Okay, so both of these observations we know by a homework problem. Okay, so remember, the result in the homework problem was that if you have an orthogonal operator, and you have W1 as in T-invariant subspace, then we can look at the orthogonal complement, right? The restriction to the orthogonal complement is also T-invariant, and sorry, it's also orthogonal, and the orthogonal complement is going to be T-invariant as long as the subspace W1 itself was T-invariant, right? So if you have these properties for W1, the same properties hold for the orthogonal complement, as long as T is an orthogonal operator. All right, so we have this. But now, again, so what is the dimension of the orthogonal complement? So the dimension is again given by the formula I already wrote earlier here, right? So now let's just express the dimension of the orthogonal complement, W1 perp. So this is just the dimension of V minus the dimension of W, right? And this is strictly less than n. Yeah, because W itself has dimension at least one, right? Remember, the dimension of W is between 1 and 2. Okay, so this is greater or equal than 1, and this is n. So we get that this is strictly less than n. Okay, but so we have a subspace which has dimension strictly less than n. Okay, and the restriction of T to this subspace is an orthogonal operator. So this means that we can apply the inductive assumption to this subspace and T restricted to this subspace, right? Okay, so let's do it then. So we may apply the induction hypothesis to W1 perp and T restricted to W1 perp. Okay, so I'm going to move to the next page. So by the induction hypothesis, we know that then W1 perp can be written as the direct sum of orthogonal invariant subspaces, right? So this means that there exist pairwise orthogonal T invariant subspaces W1. In fact, W1 we're already using. Let's start now enumeration from W2, let's say. So W2 through Wm, all subspaces of W1 perp, right? Such that the dimension of each of them, so the dimension of Wi is between 1 and 2, for I ranging between 2 and m, and such that the whole space W1 perp can be written as their direct sum. So it's W2 direct sum, etc. direct sum Wm. Okay. So strictly speaking, we should have said here T restriction to W1 perp invariant, right? Because we're just applying the theorem to that subspace. But we can say T invariant because if it's a subspace, which is W perp invariant, W1 perp invariant, remember how TW1 perp is defined. It's just the restriction of T to a subspace, right? So then it means that it's in particular T invariant, just because being contained in the subspace, W1 perp, and being invariant with respect to the restriction of the operator to the subspace, it's actually T invariant as well. Okay, so just a little point here that strictly speaking, if we just literally applied the inductive assumption, it would only tell us that it's TW1 perp invariant here, right? But it makes no difference because this is just the restriction of T, so it's also T invariant as well. Okay, so we have these subspaces, and now we hope that if you take all of this together, this is what we wanted, right? So the conclusion is that then W1, W2, etc., Wm are pairwise orthogonal So how do we know this? Okay, let's be careful here. We know this because each of Wi is contained in W1 perp, right? So this tells us that, well, for I between 2 and m. So this tells us that each of these Wi is orthogonal to W1, but we also know that they're pairwise orthogonal between themselves by the inductive assumption, right? So they're here pairwise orthogonal. So then this tells us that all of these subspaces, W1 through Wm, are pairwise orthogonal, all right? And finally, we also know that we can write V, the whole space V, the direct sum W1 plus W1 perp, okay? So this we know, again, this is just a general result about orthogonal complements. This was theorem 6.7. But now we know that W1 perp is the direct sum of W2 through Wm. So what we get is that this is W1, direct sum W2, etc., Wm. Okay. And this shows that we have proved the theorem for n, for dimension of v equal to n. So we proved the inductive step, and hence we proved that the result holds in all dimensions. Okay, so this concludes the proof of the theorem. So again, the idea was to use induction. First, you find a single subspace of the whole space V of dimension between 1 and 2. And then we'll look at the orthogonal complement of it, to which we can apply the inductive assumption because its dimension is smaller. So then you split the orthogonal complement into a direct sum of some invariant subspaces of dimensions 1 and 2. And because it's an orthogonal complement of W1, we get a direct sum decomposing the whole space. Yeah, just a quick recast of the strategy of this argument. Okay, so this proves the theorem. So now, okay, so far it's telling us that the whole space can be decomposed into direct sum of invariant subspaces of dimensions 1 or 2. Let me see, there's a question in the chat. Sentence, there exists such pairwise. Did we use the assumption? Yes, exactly. This is the inductive assumption. So on the previous page, okay, unfortunately I switched the page in the middle, I guess, yeah. So we observed that the dimension of the orthogonal complement is strictly less than n. And so we apply the induction hypothesis to this W1 perp, which has dimension strictly less than n, right? So we can apply induction. And now I just write out what the inductive hypothesis tells us when applied to W1 perp. Yeah, okay, cool. All right, so we need some more information about this decomposition of the space into as a direct sum that we get here. So this is going to be the content of the next result, theorem 647 prime. So let T V W1 through Wm be as in theorem we just proved, so as in theorem 646, okay? And we need some more results about this decomposition, about how W1 through Wm interact. So we have the following additional properties here. So first of all, T restricted to Wi is either rotation or a reflection for each I between 1 and m. Okay, so you see we get this, we now start connecting to the aim. We're trying to show that every orthogonal operator T on a real linear product space can be written as a composition of rotations and reflections. All right, so what we did, we decomposed the whole space as a direct sum of subspaces. And now we look at what our operator does when restricted to each of the subspaces in this direct sum. Okay, and part A tells us that each restriction to each of these subspaces is going to be either rotation or reflection. Okay, so it's already promising. Part B, the number of these subspaces, the number of Wi's for which TWI is a reflection is even if and only if the determinant of T is equal to 1, and it is odd if and only if the determinant of T is equal to -1. Okay, so now we are connecting the determinant of T, whether it's 1 or -1, to the number of reflections appearing among these restrictions, TWI in part A. Okay, and finally part C, it is always possible to decompose V into a direct sum as in Theorem 646, so that the number of the subspaces Wi appearing in this decomposition, for which the restriction Twi is a reflection so the number of this Wi is 0 or 1. Okay, and this is according to whether the determinant of T is equal to 1 or to minus 1. Okay, and furthermore, if Twi is a reflection, then the dimension of the corresponding subspace Wi is 1. Okay, so let me just comment what we're saying in this part C here. So the main point to understand is that the decomposition, like in Theorem 646, of W as a sum of T invariant subspaces between dimensions 1 and 2, this decomposition is not unique. Okay, there might be two different ways to write the whole space V as a direct sum of some T invariant subspaces of dimensions 1 and 2. So this decomposition is not unique. There can be different ones. Okay, and so what we are claiming in C is that we can always choose one with an additional property, that only one of the restrictions is a reflection, at most one. So could be 0, could be 1. Okay, we're not saying it's true for every decomposition like this, but only that there exists a decomposition like this. Okay, all right, so this is the theorem. So this tells us a lot about the operator T, as you will see in a second. Okay, so first let's look at part A. Okay, so proof of A. We know that each Wi has dimension which is either 1 or 2, right? So yeah, for each I. Okay, so it's either one-dimensional or two-dimensional. Okay, and T restricted to the subspace Wi is orthogonal. Okay, so this tells us that we can actually apply a result we have proved earlier for orthogonal operators on real inner product spaces of dimensions 1 and 2. Right? So remember, we treated two cases earlier in the lectures. We analyzed the case when the dimension of the space is 1, and we proved that every orthogonal operator is a rotation or reflection. And we proved the same for every inner product space of the real inner product space of dimension 2. All right. But now if I restrict to one of the Wi's, I have an orthogonal operator, Twi, living on a subspace of dimension 1 or 2. So this means I can apply those cases, right? So then we have that Twi, so T restricted to Wi, is a rotation or reflection by example in the lectures if the dimension of Wi is equal to 1, and by theorem 645 if the dimension of Wi is equal to 2. Right? Okay. So this allows we utilize the previous results. So this gives us a restriction of T to each of the Wi's is either a rotation or a reflection. Okay. Next, part B. Okay. So this time we want to show that this corresponds to the property of the determinant being 1 or -1. Okay. So let R denote to the integer R denote the number of those WIs for which TWI is a reflection. Okay, so we know that each TWI separately is either a rotation or a reflection. So just count those which are reflections and let R denote the number of them. Okay, but then by homework, we know that the determinant of T can be written as the determinant of TW1 times the determinant of TW2, etc., times the determinant of TWM. Right. So remember, we know this. If the whole space is direct sum of subspaces, and we have an orthogonal operator, then the determinant can be calculated as the product of the determinants of the restrictions. Okay. But so what is this? What is the determinant going to be? So as for each WI, which is a reflection, right? We get that this is -1, and for which TWI, which is the rotation, we get 1. Okay. So then the product is going to be -1 to the power R. Okay. So we get 1 to the power m minus R times -1 to the power R. Right? Okay, but of course we can ignore this 1 to some power because it's just going to be 1. So this is the same as -1 to the power R. Okay, and then of course this is going to be 1 or -1 depending on whether R is even or odd. Right, and this is precisely what B says. So this gives B. Yeah, because it shows that if R is even, if the number of WI for which TWI is a reflection is even, then R is even, so we get a 1, and otherwise we get -1 if it's odd. Okay, so this just comes from this. Okay, and let's finally prove part C. So I pause for a second, and then I switch the page. Let me know if there are any questions so far. Part C requires a bit more work. So you see A and B were just combining the results you already know. So part C, we need to do a bit more work. So let's try to understand what goes on here. Okay. So in this case, we let E consist of all those vectors X and V such that T of X is equal to -X. Okay, so far I'm just defining a set E like this, consisting of all vectors, for which T of X is equal to -X. So what can we say about this set? So first we can note that this is a T-invariant subspace of V. Okay, so I'm not going to write to check this carefully. You should check it. So we know how to check that something is a subspace and also that something is T-invariant. Yeah, it's not hard to verify from the definition in this case that we get a T-invariant subspace. Okay, so now if we had that W is equal to the orthogonal complement of E, yeah, so let's denote by W the orthogonal complement of E. Then we get that W is also T-invariant, T-invariant subspace, right? So this is again by the homework problem. Okay, so the orthogonal complement is T-invariant. Now we can apply the theorem, the decomposition theorem, to T restricted to the subspace. So applying theorem 646 to T restricted to W, an orthogonal linear operator on W. So here I should stress that, moreover, TW is also is orthogonal. So this is by the same homework problem, right? We know that T is invariant. The orthogonal complement of an invariant subspace is invariant, and the restriction of an orthogonal operator to it is still orthogonal. Okay, so this means we can apply theorem 646 to this operator, TW, the restriction. Then we obtain pairwise orthogonal T invariant subspaces W1 through WK, all subspaces of W, such that the whole space W can be written as a direct sum. So W1 direct sum through WK, right? And the dimension of each of these WI is between 1 and 2. So just apply the theorem to this subspace. Okay. So now let's analyze. So again, look, this gives us a decomposition, right? But the only point is that we are taking the decomposition like in theorem 646, but we're doing it a bit more carefully. We're starting not with anything, but we are starting with the orthogonal complement of this particular subspace E. And you'll see how it's useful when we finish. So the point is that we only need trying to show that we can only get one reflection in the resulting decomposition, which is going to correspond to E. Okay, but let's return to where we are. So we found this decomposition of W. Okay, so now I'm claiming that each TWI is a rotation. Okay, so we don't have any reflections among the TWIs here. Okay, why is this the case? Well, if assume towards contradiction that TWI is a reflection for some I, this would mean that there exists some X non-zero vector in this subspace WI such that T of X is equal to minus X, right? That's just by definition of reflection. Okay, but then this X is going to belong, so it belongs to WI by assumption, right? But it would also belong to E. So it belongs to the intersection of WI intersection E by definition of E, okay? But this is a subset of the orthogonal complement of E intersection with E, right? Because remember, WI, this is a subspace of E orthogonal complement by definition of W, right? So W equal E orthogonal complement. So we get that X belongs to E intersection with its orthogonal complement, but of course we know that this intersection is zero. For any subspace, if you take the intersection of the subspace with this orthogonal complement, you only get zero. Okay, so this shows that X has to be zero, but this is a contradiction because we assumed that X is a non-zero vector here. We chose a non-zero vector. Okay, so a contradiction. Okay, so this shows that indeed each of the TWIs is a rotation. Okay, so now we have to make sure that, but the WIs, they don't yet give the decomposition of the whole space, right? They only give a decomposition of W. So now we need to extend it to a decomposition of the whole space as a direct sum. So there are two cases. First case that this subspace E that we started with is trivial. It only contains 0. Well, then the result follows. So then C follows. Because we don't have any reflections, right? Because then we already have that V is equal to the direct sum of W1 through WM, WK, we denoted it, sorry, WK, and each TWI is a rotation, right? So in this case, we got no reflections at all. So we decompose the whole space so that all TWIs are rotations. So reflection can happen if E is non-trivial. So assume then that E is a non-trivial subspace. All right. So we need to conclude this case now somehow. All right. So if it's non-trivial, then we can choose an orthonormal basis. Beta for E for this subspace, right? Containing some vectors. So let's denote it by P, the dimension of this subspace. So containing P vectors for some P greater than 0. Okay. So we assume it's non-trivial. So its dimension is finite, but not 0. So we pick a basis, an orthonormal basis. Okay. Now we can write beta, this basis, as a disjoint union beta equal to beta 1 union beta 2, etc., union beta R, such that we have the following. So each beta I contains exactly 2 vectors for I less than R. And the second point, the last set in this union, beta R, contains 2 vectors if P is even, and it contains 1 vector if P is odd. Okay. So this part, I mean, it's a very easy claim, actually, if you think about it for a minute. Because look, assume we're given some set, right? Like I'm given some set of elements. This is my beta. So how do I choose beta 1 through beta R? Well, I just start picking them one by one. So assume I have, like, I can take beta 1 to be any 2 vectors if I have them. Then I take beta 2 to be any 2 vectors, etc. So I keep doing it as long as I can. And eventually I'm left with either 1 vector or with 2 vectors, right? And then I can take beta R to be these 2 vectors. And if I only had 1 vector, I just take beta R to be that 1 remaining vector. So if I had 1, I take 1, okay? And this corresponds precisely to whether P was even or P was odd, whether the last beta R is going to be 1 vector or 2 vectors, right? So I just try to partition the whole space into a union of 2 sets of size 2, and then I'm either left with 1 vector or with 2 in the end. And so depending on whether the total number of vectors was even or odd. Yeah. Okay, and you can pick this beta 1, beta 2 any way you want, as long as they, well, following the requirement that they contain 2 vectors if you can. Okay, so this gives us such a presentation of beta as a union of some subsets. Okay, so now what do we have from this? Okay, so for each I ranging between 1 and R, we let W k plus I be the span of beta I. Okay, note here that the enumeration, we are starting the enumeration from K because we already have W1 through WK. This was the decomposition of V. And now we are trying to decompose the remainder. So we are trying to decompose E now. And so this, remember, the sum of W and E is the whole space. Okay. So then we define WK plus I like this. Then we have that W1, W2, etc., all the way through WK plus R. Okay. So we have more spaces now. So all these are pairwise orthogonal. Okay, how do we see that they're pairwise orthogonal? So we knew it for the first K from the choice here, right? We know that these K subspaces are pairwise orthogonal. And for the new ones that we just added, we know this because beta was an orthogonal basis, right? Beta, all of beta was an orthogonal basis. And so if we take the spans of some disjoint subsets of this basis, so we took the span of vectors corresponding to this, etc., and then to this, then they're still orthogonal, right? So we know this. And all of them live in E, right? So all of these are subsets of E. So note here that WK plus I is a subset of E. And remember that W was the orthogonal complement. So J is contained in E orthogonal complement for J between 1 and K, right? So we see that each of the new spaces, subspaces, is orthogonal to each of the old ones that we had before. So this means all of them are pairwise orthogonal. So you have to check these two cases, yeah? But we get that they're all pairwise orthogonal. Okay, this is good already. And we can write the whole space V as the direct sum of W plus E, right? Because W is simply the orthogonal complement of E. Okay, and now we can plug all the subspaces. So we get that this is equal to W1, direct sum, etc. Direct sum WK, direct sum WK plus 1, etc. all the way through WK plus R. Right? So we have obtained a decomposition of the whole space as V as a direct sum of pairwise orthogonal subspaces. So let's denote this equation by star. Okay, it wasn't a good star. Okay. All right, let me pause here because there's a lot going on. So we decompose the whole space into direct sum of pairwise orthogonal subspaces. And we know that restriction of T to each of the W's among the first K ones, so up to here, right? We know that the restriction is a rotation. So now we have to show that at most one restriction of T among the remaining ones here is a reflection. We have to show that there exists at most one which is a reflection among them. Okay, so I'm going to do this on the next page after a second. Yeah, let me know if there are any questions at this point. Okay, how do we know that for beta I, each one contains two vectors, except the last one? Yeah, exactly. So that's what I was trying to explain in this picture. We know it just because we choose them like that. Like imagine you have a set, for example, with 3 vectors. Let's say beta has 3 vectors. Then I just try to split it into pairs any way I want. So I just pick any 2 and I say, this is my first pair. Okay. Let's say I had 5 vectors. Then I can pick some other 2, for example, these ones. This gives me another pair. Okay. But then I'm still left with 1 because I have 5 altogether. Beta I basis for WI. Yes, by definition, right? Because we start with a basis for the whole space E. This is beta. And then I cut it into pairs. I split it into pairs and possibly 1 that remains if there's an odd number of vectors. And then I take WI simply be the span of beta I. Here, right? So we just define WK plus I to be the span of the corresponding pair. So so it's going to be basis automatically because the beta was a basis. So take the span of a pair of vectors from the basis for each pair. Thanks for the questions. Yeah, it's good. Ask me, everyone, please feel free to ask me if anything is unclear. So, right. So the point here, we just choose to do it like this, right? Like it's not this beta I, they're not given to us from the sky or something. We choose them. So we just try to choose them any way we want, but making sure that we pick two as long as we can. Like we just, like, for example, I pick beta 1 to be like first vector and second vector. Then I pick beta 2 to be third and fourth, etc. Until I'm stuck. And if then I either exhausted all the vectors in beta, or I'm left with one, which I cannot pair with anything, and then I just take it as beta R of size 1 in the end. Okay. Yeah, it's just, we just try to choose it by like this explicitly. All right. So anyways, so we have V decomposed to the direct sum like this. Okay. So now we want to conclude. So if any beta I contains two vectors, then we can look at the determinant of T restricted to the corresponding subspace. Yeah, so beta I is the basis for this subspace. Then the determinant is going to be the matrix representing this restriction to beta with respect to the basis beta I. Okay, and now this is going to be, here we should remember how E was defined. So we have T of X is equal to minus X for all vectors X in E, right? And this subspace, it is a subspace of E. So we get that the matrix is going to be minus 1, 0, 0, minus 1. Yeah. And this determinant, of course, you can see it's equal to 1. So for each beta I, which contains two vectors, we get that the determinant is 1. And so we know that T, in this case, when beta has two vectors, we get that T restricted to WK plus I is a rotation, because it's two-dimensional, and the determinant is equal to 1. Hence, we get that TWJ is a rotation for all J less or equal than K plus R, right? Because again, we chose this beta I so that all but the last one have two, well, we know that first K are rotations by the choice of the WI for I smaller than K. And among the new ones, we have shown that all but the last one contain two vectors. And so all but the last one are rotations, yeah, guaranteed to be rotations. Now, the only remaining point is what happens to beta R. So if beta R consists of a single vector, of one vector, then we get that the dimension of WK plus R is 1, because it's the span of the single vector. And the determinant of T restricted to WK plus R is going to be the determinant, again, of the matrix representing T WK plus R with respect to the basis beta R, right? And this is equal to the determinant of the one-by-one matrix consisting of minus 1. This is again because T of X is equal to minus X for all X in E, right? And this is still, as in the previous line, a subset of E. And so this is minus 1. So in this case, TWK plus R is a reflection by example 1, right? Because we have a one-dimensional, because in this case, WK plus R is a one-dimensional space. TWK plus R is an orthogonal operator on it, and the determinant is minus 1. So from that example, we considered for one-dimensional spaces, it is a reflection then, okay? And so we conclude. So hence, the decomposition star that we have here on the previous page in the corner, yeah, this decomposition satisfies C. Because we have shown that at most one of the restrictions to a subspace Wi is a reflection, right? Because there's only at most one beta which contains one vector. Could be 0, could be 1. So it shows that either we have at most one reflection or we have no reflections at all if the size of beta was even. Yeah. And this concludes the proof, right? So we have shown that we can choose a decomposition, which we need to be a bit more carefully than in the proof of 646, because now we started with E, not with an arbitrary subspace. We can choose such a decomposition which contains at most one reflection for any orthogonal operator. All right, and so we are almost done. So what remains now is actually to collect some final piece of information about this decomposition, which will allow us to conclude that T, any orthogonal operator T, is a composition of rotations and reflections. So we have almost everything ready for it, and we'll finish this next time. Yeah, sorry for taking some extra time here. So